Hello, my name's Phil and I'm the designer and builder of robots for Team PiDrogen. In today's video I'm going to talk about how we approach building robots for Pi Wars. Our robot is designed as a base unit which is kind of game independent and which provides all basic robot functionality. And then there's separate implements which are built for the particular games. So in this video I'll talk about the base robot and then go on to the game implements which we've built for tidy up the toys and feed the fish. And then finally I'm going to talk about Fusion 360, because our robots, well, everything that we've built is all designed in Fusion 360, and I think it's a very good way of proceeding to build these sort of things. So I hope you enjoy the video. I'll start off with a talk about the base robot. This is our robot. We call it P21. Here it is under radio control with balloon tyres fitted. These tyres give the robot the best obstacle clearance capability. P21 chassis is designed in Fusion 360 and is all 3D printed. It's the second rework of our robot since the 2019 games. For this machine, the main philosophy is that the core robot is as general purpose as possible. We can then add game-specific implements to address the particular disciplines within the competition. To achieve this, the top of the robot is flat with mounting holes built in. The holes have captive nuts behind them so that an implement can be quickly and reliably screwed in place. There is an electrical interface presenting various voltages and a two-way serial bus to the main robot. The underside of the robot has a similar system. We can swap wheels for the different challenges: big balloon tyres for good obstacle clearance, Mechanon wheels for omnidirectional moves, which were mainly used for Pi Noon, or smaller wheels for the more delicate manoeuvring. For most autonomous games, we plan to use smaller diameter wheels. This is P21 with its lid removed. I've completely redesigned the electronics for P21. Our 2019 robot had the Pi and touchscreen mounted on the back of the robot. P21 has the Pi mounted inside the lid, so it's less vulnerable. The robot uses an Arduino which connects to the Pi via the serial port on the Pi header. The Arduino interfaces to the various robot components, so the Pi does not need to be servicing time-critical interrupts. The robot has an IMU to measure its orientation in the world, and a radio receiver for the remote control challenges. P21 uses motors with encoders which allow more delicate control and also allow moves based on odometry. 3 time-of-flight sensors are mounted on the front, one facing forward, one to the left, one to the right of the robot. A small screen and keys on the back axle permit game selection and start-stop signals to be issued without a Wi-Fi connection. The Arduino collects updates from the various sensors and the back screen and then sends them to the Pi 20 times a second via the serial connection on the Pi header. The Pi issues commands to the robot via the same serial connection. Our 2019 robot had the Pi and touchscreen on the back, which we could use to configure the robot's software. When we moved the Pi inside the hull, we reworked the software so that it can be controlled via an IP socket interface instead. This is a video capture of the PC program which connects to the socket interface. It displays marked up images from the camera and allows control of the game and software parameters. Here you can see the view from PiDrogen's camera as it follows a short section of line. The coloured blobs on the line show that the Pi is interpreting the location of the line. It marks up the camera feed to assist with debugging and vision of the software. The robot follows the line, does a 180, follows the line back, then finishes with a final 180. This is the gameplay we use for developing line following, since the robot always returns to the start position. Well, hopefully anyway. The robot software is written in Python and uses OpenCV for video processing. It is structured as a framework which provides all the foundational class functions to a base class called GameBase. Then individual classes are derived from the base class and instantiated in their own thread. These provide the game-specific functionality. The GameBase class offers a series of fundamental functions. For example, it can make turns of a specified angle or onto a particular heading. It can accelerate or decelerate with a particular profile onto a specified speed. It can drive for a particular distance or until its time of flight sensors tell it to stop. The base class also provides some video controlled moves. For example, the robot can steer itself towards a target of a particular colour. These functions can all be combined. For example, the robot can drive towards a colour and come to a stop when the front time of flight measures a predefined value. As I said earlier, the idea is that we have a general purpose robot on which we can build further game-specific implements. Let's take a look at the first game implement, the Feed the Fish catapult. This is P21 with the Feed the Fish catapult attached and the small wheels fitted. We hope to tackle Feed the Fish by lobbing projectiles into the top of the aquarium, since this attracts most points. And since the game is against the clock, we will fire 5 rounds at a time and have made reload as straightforward as possible. The design is an elastic band powered catapult which shoots Nerf rival balls, as suggested on the PiWars website. It is mounted on a turntable so that it can be aimed without moving the whole robot. We can adjust the tension in the rubber bands to alter the power in the catapult, and we can change the arm end stop to change the trajectory of the projectiles. We are using video guidance to align the robot with the aquarium and the front-facing time of flight sensor to set the distance of the robot to the aquarium. For some reason, the catapult shoots to the left, so we use the turntable to aim to the right. Reloading is a case of placing the balls in the cups and then clicking the arm into position. This is the third design for this device. The first used this shape of catapult arm, but we found that the ball at the end of the arm goes much further than the inboard one, so you can't tune the system. Placing the projectiles in a row makes them all fly with a similar trajectory so that they can all hopefully land in the aquarium. The first design was mounted sideways on the robot so that it would shoot to the left. The idea was that the robot would drive directly across the arena without making any turns. This is quick, but it leaves the catapult too far from the target. So the current design fires forward. This allows the robot to get closer to the target and also allows the use of video guidance to aim the shot, but the robot has to turn when making the move from the loading area to the firing position. Of course, we are hoping to get all 15 balls into the aquarium. This design can get 5 balls in at once, but not reliably so. 3 consecutive clean shots would be lucky. More work is needed to make the catapult more consistent. Now let's take a look at Tidy Up the Toys. This is the toy box lift I built for Tidy Up the Toys, and I think it's probably the hardest build of anything PiWars related. Again, we are seeking to maximise points in the game, so we plan to pick up all 3 boxes in the correct order and deliver all 3 at once as a stack. This is why the jaws on the left are so tall. The design has a couple of arms mounted to the top of the robot. The arms have a track to guide the lift and a rack that the lift climbs. The moving part of the lift has a small motoring gearbox attached to a couple of Lego pinions which engage with the racks. A light beam is used to detect the bottom of the lift travel, and the motor has an encoder so that the height up the rack can be measured. A normal servo grips the boxes via another Lego gear train which synchronises the jaw movements. The robot camera looks between the arms and it can see under the lift when the lift is raised high enough. This allows video guidance to be used to align the robot on the boxes. Unfortunately, P21's existing front-facing time of flight sensor is set too high on the body, so it looks over the top of the toy boxes. So the toy box lift has its own time of flight sensor fitted. This is used to stop the robot in the right place for picking up a box. The game strategy uses a mix of odometry-controlled moves and IMU-controlled turns to manoeuvre around the arena. Video and time-of-flight controlled moves are then used for precision alignment on the boxes. Once the boxes have been collected, the final move to the end zone is measured by the front-facing time-of-flight sensor. Here we can see the system picking up 3 boxes in a row. This isn't the full gameplay, but it allows us to test the tricky elements of the game with power supplied from a bench power supply. This is much easier than constantly swapping lipos. And by tricky elements of the game, I mean aligning on the boxes well enough that one can be placed on another. You may have noticed that P21 makes rather slow moves all the time. This is deliberate for testing. Tests frequently go wrong, and slow speeds give me time to hit the stop button. However, I think we're basically ready to record the final video for this competition, so I'll start cranking up the speed of the simple moves to see what impact this has on the overall game times. Okay, now I'd like to talk about Up the Garden Path. What you're seeing here is a a clip of video from the point of view of the robot's camera. So what I've done is use the robot to record a video clip of the robot following a line. The reason I've done this is because the 2019 software was unable to resolve junctions. It didn't need to do junctions. Obviously, with the new game, we have to be able to work out where there's a junction and which way to go. So I've been working on the software to make it detect junctions. So what I've done is record a video from the robot, and then I can play that video through the software for the robot, but on a PC, and record the output of that process back into a new video. And that's what you're seeing here, that new video. I've then just got it on a video viewer so that we can slow it down and take a look at it frame by frame. So what you're seeing here is the line out the front of the robot, and just ahead of us is a branch coming up, a fork in the road. Then we have some coloured lines painted over the top. Now, the idea is that these coloured lines, if I drag the thing forward, so now I've lined those lines up on the junction that's ahead of us. And the way this works is the software looks under those lines to see how much of the black line on the floor exists under each of the colours. So the green line there, you can see, if you look at the green number down here, it's showing 713. Now, let me back it up again. So as we approach the junction, the green number's on 167. As I get on top of the junction, you can see it's jumped to 713. So there's 713 pixels under the green line, which are the black line color on the floor. So the way the software works is it detects that as a route out of the junction. You can see that also there's a big number on the red because there's an option to go towards the red. The pink's down low at 190 because that's not this type of junction, so that's not relevant for this one. And again, straightforward in white is only 172. So you can see that what happens here is that the software uses this system, and when it sees those numbers jump, it knows it's got a junction ahead of it. It can then, the idea is that software will know the route to go already, either because I've programmed it in or because I've told it verbally. So as it approaches the junction, it can take a decision to go left or right, whichever is necessary. It's still very much a work in progress. It is able to detect junctions, so my next step is to get it working nice and quickly on the real robot and making sure it's fairly robust. So I'm going to stop there because that's about as far as I've got with the junction detection, and I'm going to move on to the next section of this video. So now I thought I'd show you how I've gone about developing PiDrogen in Fusion 360. Here is the Fusion 360 model of P21. You can see that there's a lot of detail gone into this model. All of the components are built into it. If I, for example, switch off, if I make the lid transparent, you can see inside the robot there. Let's get rid of that. There's the Raspberry Pi. I'll take that out as well. That's the camera. Hang on. There's the Raspberry Pi. Let's turn that off as well. Get that out of the way. So now you can see inside the robot. There's the motors for the two front wheels. This black box here is the LiPo. It's quite a lot of detail. There's you can see the back of the switch there, look, for the on-off switch. So what I wanted to do was a bit of the video just to explain how I've gone about building this model, and then from that building the actual robot itself. So the first step to doing this is to model the components. PiDrogen's built of, with lots of components. The motors we were looking at, I'm going to zoom in on those a bit. Those are motors off the shelf, and obviously then not something you can change. So the first step, I think, is to build models, 3D models of those components in Fusion. And you can look here. This is one of the motors which I've modeled in Fusion 360. There's one of the servos that's being used. Now, those are ones that I've modeled. I can't get to my, let's get rid of that. There we go. So those I was showing you earlier were models I've made. This is one I've downloaded. So this is the Raspberry Pi camera, and it's brought off of the Fusion gallery. So someone else has modeled this. They've done a lot more detail than I normally bother with. It looks just like the real part. So what I've done here is either modeled components or ideally collected online components, so that I've got the collection of the parts that I need for the robot. But mostly you have to do these things yourself. So what I thought I'd do is show you just very briefly how I would go about modeling this motor. I won't do all of it, and I won't do it in much detail, but I'll do enough that you get an idea of what's involved. So what I'm going to do is say new design. I've got a blank sheet of paper in effect. I'm going to select the elevation I'm going to draw on, and then I can create a sketch. That's the first step in Fusion. And it's asking me in what plane I want to draw. So I'm going to draw onto the front of the motor. Now, I'm going to set about drawing that front elevation. So what I'm talking about here is looking end on to the shaft. So the shaft is a 4mm shaft. So there's a 4mm circle I've drawn. There's then a bush. I'm actually consulting a diagram that you can't see. There's a 7mm bush, and then the outside diameter of the robot is 25mm. So let's put that on there. Let's move those dimensions out of the way, try and tidy this up a little bit. There we go. And I can zoom in a bit now. Now we know what size we're dealing with. There's a couple of mounting holes in the end of the motor. So let's put a circle on. I'm going to guess at this. Obviously, if I was really modeling it, I would be very careful to get these sort of things correct. I'm going to put the mounting holes in there, M3. So there's a 3mm hole. Let's grab that dimension and get it out of the way. Another one down here. I can drop a line from the center of there and it will click into place. 3mm again. So I'm just trying to pick up that dimension to get it out of the way. There we go. So I think that's enough detail just as a start, just to get the end of the motor. So I'll finish that sketch. I'm just showing you what I'm doing. Effectively, we're looking onto the end of the motor there. Let's extrude that. The diagram I've got here says that the shaft comes out 12mm. So let's extrude there, make that 12mm, and there we have a shaft modeled. And Fusion's done the thing where the first time you extrude from a sketch, it disappears the sketch. It makes the sketch invisible, which is a bit disconcerting if you're new to Fusion. I shall put that back on and extrude the bush that's on the front. That's 2.5mm thick. I'm going to say it's offering me to join it all up in one, but I'm going to say that's a separate body. I tend to make all these components into separate pieces and join them all up at the end. I think that's just a matter of taste, but that's how I like to do it. I'm going to extrude the end of the gearbox now. I'm going to include the holes. And the gearbox itself is 21mm long. I want it to extrude the other way, so I'm going to say -21. And there we have sort of the gearbox taking shape. I'll put the holes in, extrude again, pick up all these pieces. I'm going to say, I don't know, -15 or something. This time you get like a red symbol that means it's doing a cut. So there we go. I think you get the idea. That's kind of a gearbox modeled. I won't go any further, but eventually you can create a model which looks more like this. And the next step, so we gather all those components together. The next step is to put them into a new design. Now, I've done this earlier to try and speed things up. I've collected a bunch of components. So what I've got here, so I've got obviously got those wheels. Let's turn those off, make them disappear. And we've got a lipo. We've got one of those motors. So let's get the motor. Now these symbols are the origin. Now what I'm going to do is make the robot symmetrical about this plane. So that's the kind of from front to back type plane. Let's move this motor so that it's only is on one half of the robot. So we'll move this over. I can grab hold of that and move it. You know, I'd do this a bit more carefully if I was actually doing it for real, but let's go say 65, 70, let's make it 70 millimeters. There we go. So there you can see I've got the center plane of the robot there, and then this robot is on one side. And when I'm satisfied that the position is correct, I can make a mirror image of that motor in this case. Mirror, I'll capture position, I'm going to mirror that device. The mirror plane is this, and we get ourselves a pair of motors. Let's turn those wheels back on, which I've imported from one of my designs. Obviously, they're now in the wrong place, so let's set about putting those in the correct place. I can move the wheels. Let's select the wheels there, and let's do that one first, the mirror one. And I've selected the rim and the tyre. I think we moved it by 70, didn't we? So if I say minus 70, that's kind of shifted perhaps moved it a bit too far, but anyway, so you get the idea. So let's put the wheel out there. Let's do a similar thing on the other side. Rim and tyre selected. Minus 70 again. There we go. So I think you can see that there's kind of an axle taking shape there. Let's put that lipo back in. And so the process goes on, and you end up with all the components placed in the robot, and you can sit and shift them about and switch places and turn them over and put them around the other way and do all sorts of things until you feel like you've packaged the whole thing together in a sensible way. When you're happy with it, then you can set about building the chassis around the thing. So as you can see, I've located all those components in there the same way, and then I've designed this chassis to sort of combine it all, and it's been designed to be 3D printed. So you know, the whole thing has been put together that way. And then you know, the reason this is so wonderful is, you know, when I'm satisfied that the chassis is in a good shape, I can go to the hull, which is the bit I'm talking about here, and I can select the whole body, which is that, and I can right click on it and export it, save it as an STL file. And that's wonderful because that means I can then put it straight through to the slicer software and 3D print it. And you know, where I've drawn the dimensions of those motors onto this component, I can expect it to print with the holes in the right place, so I can literally screw the thing together, put the motors in place and screw them in place with some M3 screws. So, you know, it's pretty wonderful how you can manufacture something like this. Trying to manufacture this by hand would be dreadfully difficult, but I can sit and leave the printer to do it overnight and job's done. So there you go. That's why I'm a big fan of Fusion 360. As I said to you, I've developed all of the robots I've developed all the robots we've built in Fusion 360, pretty much learning 360 as I went. So it's for me, that's a bit of a secret weapon of how we've built these robots. I'll stop there. Thanks for watching. Well, I think that is all I have to say for now. If you want to know more, take a look at our blog on PiDrogen.com or follow us on Twitter. Thanks very much for watching. All that remains is to wish all the competitors good luck in the competition, but most of all to say a big thanks to Tim, Mike, Dave and Rob, and anybody else who helped in the organisation of the competition. We all really appreciate it. Thanks very much. Bye for now.